In this video, we're going to start Chapter 13, Partial Differential Equations. So in this chapter, we're going to cover an introduction in this video here. We're going to discuss elliptic PDEs, parabolic PDEs, hyperbolic PDEs, and then finish with some discussion of semi-discretization. And the content for this chapter came from largely from these references here. So a partial differential equation, or a PDE, is an equation stating a relationship between a function of two or more independent variables, and the partial derivatives of this function with respect to these independent variables. So there are several classic PDEs that describe various phenomena in engineering. So for example, this equation here, partial 2f by partial x squared plus partial 2f by partial y squared is equal to 0 is the 2D Laplace equation. This shown here, partial f by partial t is equal to alpha, partial 2f by partial x squared is equal to 0 is the one-dimensional diffusion equation. And what's shown here, partial 2f by partial t squared is equal to c squared, partial 2f by partial x squared is equal to 0 is the one-dimensional wave equation. As a matter of notation, we can also write these equations in this form, where the subscripts denote the partial derivatives with respect to those variables. So f subscript xx means partial 2f by partial x squared, and f subscript yy is partial 2f by partial y squared. So the solution of a PDE is the particular function f of x and y, or f of x and t, for example, that satisfies the PDE in the domain of interest, where the domain of interest could be d of x and y or d of x and t, respectively, and satisfies the initial and or boundary conditions specified on the boundaries of the domain of interest. The order of a PDE is determined by the highest order derivative appearing in the equation. So for example, this equation is second order, because the highest order derivative is second order. A linear PDE is one in which all partial derivatives appear in a linear form and none of the coefficients depend on the dependent variable. So for example, all of these PDEs are linear. This one here, we see that we do have a variable coefficient. So assuming that alpha is a constant, a is a constant, b is a constant, here we do have a variable coefficient x, but the variable depends on the independent variable, not on the dependent variable. A nonlinear PDE is one in which the derivatives appear in a nonlinear form, or the coefficients depend on the dependent variable. So for example, both of these are nonlinear PDEs. You can see that here the coefficient depends on the dependent variable, and here the derivative appears in a nonlinear form. A homogeneous PDE is one in which all of the terms contain the dependent variable or its partial derivatives. So for example, if we bring everything that contains the dependent variable or its partial derivatives to one side of the equation, we're left with the 0 on the other side of the equation. A general example of a non-homogeneous PDE is shown here. So we've got the partial derivatives on one side of the equation, and then some function of the independent variables on the other side of the equation. So the non-homogeneous term is a forcing function, a source term, or a dissipation function, depending on the application. So this particular example here is the non-homogeneous Laplace equation, which is also known as the Poisson equation. So let's talk about classification of PDEs. Let's consider the general quasi-linear second-order non-homogeneous PDE in two independent variables. A quasi-linear means that it's linear in the highest order derivative. So the classification of this general PDE depends on the discriminant, which is b squared minus 4ac, where you can see the b and the a and the c are the coefficients of these particular derivatives. So if this discriminant, b squared minus 4ac, is negative, then the PDE is elliptic. If b squared minus 4ac is equal to 0, then it's parabolic. And if b squared minus 4ac is positive, then it is hyperbolic. So this terminology, elliptic, parabolic, and hyperbolic, are chosen to classify PDEs because this reflects the analogy between the form of the discriminant, this b squared minus 4ac for PDEs, and that which classifies conic sections. So conic sections are described by a general second-order algebraic equation, as shown here. So here, instead of the derivatives, we've just got variables. So this is an algebraic equation, not a differential equation. But if we look at this same discriminant, b squared minus 4ac, we can classify these types of equations similarly. So if b squared minus 4ac is negative, then we get an ellipse, something like this, shown here. If b squared minus 4ac is 0, then we get a parabola, like what is shown here. And if b squared minus 4ac is positive, then we get a hyperbola, which is shown here. So the names chosen for the PDEs are based on this analogy between the two types of equations, based on the analogy related to this b squared minus 4ac. So why is this classification important? Well, for PDEs, the classification is important because it's related to the characteristics of the PDE. The characteristics are n-1 dimensional hypersurfaces in n-dimensional hyperspace that have some special features. So the prefix hyper here is used to denote spaces of more than 3 dimensions. So for example, x, y, z, t spaces, and curves and surfaces within those spaces. So in 2D spaces, characteristics are paths that are curved in general and in the solution domain along which information propagates. So information propagates along the characteristic paths. Discontinuities in the derivatives, if they exist, also propagate along the characteristic paths. If no real characteristics exist, then there are no preferred paths of information propagation. So characteristics have an impact on the solution of a PDE, both analytically and using numerical methods. So to determine characteristics of a particular PDE, we will answer the following question. Are there any points in the solution domain d of x and y passing through a general point P along which the second derivatives of f of x and y, so for example fxx, fyy, or fxy, are multivalued or discontinuous? If such paths, if they exist, are paths of information propagation. And so these are called characteristics. So discontinuities in the derivatives, if they exist, also propagate along these characteristic paths. So let's look at these derivatives, partial f by partial x and partial f by partial y, and use the chain rule to determine the total derivatives. So we want to know d of fx and d of fy. So d of fx, we can use the chain rule and see fxx dx plus fxy dy, and d fy is fyx dx plus fyy dy, where again these subscript notation indicates the partial derivatives. And let's also recall the relationship between the 3 second derivatives of our function f of x and y, which we had shown here for a general second order PDE. So we can write these 3 equations in matrix form here. So the first equation comes from here, and then the other 2 equations come from what we've called equation 3 here. Now we can set the determinant of this matrix to 0, and we get the equation shown here. So this is the characteristic equation corresponding to our differential equation, which we called 1. And it can be solved to yield dy by dx is equal to b plus or minus b squared minus 4ac, all divided by 2a. So this is the differential equation for two families of curves in the xy plane, corresponding to the positive and negative signs here. So these two families of curves, if they exist, are the characteristics of the original PDE. So again, we can look at the this quantity here, b squared minus 4ac, the part under the square root. If this term is negative, then the characteristic curves are complex, and the classification of the PDE is elliptic. If this term is 0, then the characteristic curves are real and repeated, and the classification of the PDE is parabolic. And if this term is positive, then the characteristic curves are real and distinct, and the classification is hyperbolic. So elliptic PDEs have no real characteristic paths. We can see that the characteristic curves are complex, so they have no real characteristic paths. Parabolic PDEs have one real repeated characteristic path, and hyperbolic PDEs have two real and distinct characteristic paths. So the presence of these characteristic paths in the solution domain lead to the concept of domain of dependence and range of influence. So if we consider a point P in our solution domain d of x and y, the domain of dependence is the region of the solution domain upon which the solution at point P, f, which we can call f of xp, yp, depends. So the solution at point P depends upon the entire domain of dependence. The range of influence is the region in the solution domain at which the solution, f of x and y, is influenced by the solution at point P. So the solution at point P, which is f of x, p, y, p, influences all of the points in the range of influence. So if real characteristics exist, then there are preferred paths of information propagation, and we have these specific domains of dependence and ranges of influence for every point in the solution domain. So physical problems governed by PDEs that have real characteristics are propagation problems. So parabolic and hyperbolic PDEs govern these propagation problems, where the information propagates along these characteristic paths. If no real characteristics exist, then there are no preferred paths of information propagation, and the domain of dependence and range of influence is actually the entire solution domain. So since there are no curves along which the derivatives may be discontinuous, the entire solution domain must also be continuous. So physical problems governed by PDEs with complex characteristics are equilibrium problems. So elliptic PDEs govern equilibrium problems. So there's no real characteristics, no preferred paths of information. So the whole domain is the domain of dependence, and the whole domain is the range of influence. So we don't really have this information that propagates, say, over time. It's just a problem that we solve everything at equilibrium. So for an elliptic PDE, the whole thing is the whole domain is the range of influence, and the whole thing is the domain of dependence. So this whole thing here is both the range of influence and the domain of dependence. For a parabolic PDE, we have this sort of division here. So where the point P, this is the domain of dependence. So the solution at P depends on everything in the domain of dependence, and the solution at P influences everything in the range of influence. And hyperbolic PDEs have these two distinct characteristic paths. So the solution at P depends on everything in the domain of dependence like this, and the solution at P influences everything in the range of influence, like this. So let's look at some examples of classifying equations. So if we have an equation here, a general second-order PDE that has just the partial derivatives and potentially a non-homogeneous term, this is the characteristic equation for this PDE. So let's first consider the 2D Laplace equation. So here you can see that comparing to our characteristic or our general PDE, if we set A is equal to 1, B is equal to 0, C is equal to 1, and G is equal to 0, then we get the 2D Laplace equation. So in this case, B squared minus 4AC is equal to 0 minus 4 times 1 times 1, so negative 4. So it's negative, which means that the Laplace equation is of the elliptic type, and steady state problems are governed by the Laplace equation. So if we want to go through and find the characteristics, we can do this by performing the characteristic analysis. So this is our PDE, and again, recall that we can take use the chain rule to find these total derivatives d of ux and d of uy. And then these three equations can be written in matrix form, as shown here. To find the characteristics, we set the determinant of this equals 0. So we get 1 times dy squared plus 1 times dx squared equals 0. So then our solution here is that dy by dx is equal to plus or minus the square root of minus 1. So this is a complex number, so there are no real characteristics. So there are no preferred paths of information propagation, which we get for elliptic PDEs. So the whole thing is the domain of dependence, and the whole thing is the region of influence. So a classic example of an elliptic PDE is the steady state heat problem in a solid. Which can be written as here. So if T is the temperature of the solid, then partial 2T by partial x squared plus partial 2T by partial y squared is equal to 0 is the PDE that governs this behavior at steady state. Along the boundary, which is denoted B, the temperature is subject to the boundary conditions, which can be described as here, where Tn denotes the derivative normal to the boundary. So equilibrium problems are analogous to boundary value problems in that we studied in ordinary differential equations. So let's look at another example. Consider the equation here with k greater than 0 and t is equal to time. So here A is equal to k, B is equal to 0, and C is equal to 0, in kind of comparing back with our characteristic equation for the PDE. So our B squared minus 4AC is equal to 0 minus 4k, which is 4k times 0, which is equal to 0. So that means this is a parabolic PDE. The characteristics, again, are determined by performing the characteristic analysis. So in this case, we've got our PDE here. We've got our, again, our equation for the total derivative d of ux and d of ut. We can put this into matrix form and take the derivative, sorry, not take the derivative, set the determinant of this matrix equals 0. So we get k d squared, or dt squared is equal to 0. So that means dt is equal to 0, or t is equal to a constant. So the characteristics then are lines of constant time. So the speed of propagation of information along these characteristic paths is given by here. So c is the speed of information propagation is dx by dt, and we said that dt was equal to plus or minus 0. So the speed here is plus or minus infinity. So the information propagates at an infinite speed along these lines of constant time. So you can see that everything kind of flows together. This whole line kind of propagates in time. So this example is known as the heat equation or the diffusion equation, the unsteady heat equation. It represents the propagation of heat, for example, in a thin, long insulated rod of unit length and uniform cross-section. So the initial temperature distribution is prescribed as the initial condition. And so this is some initial condition, which is given as just a function of x. And then the boundary conditions, say the ends of the domain, t equals 0, or sorry, x equals 0 and x equals L, are prescribed for all time. So these boundary conditions are prescribed for the whole time, and then we march forward in time on this. We have a closed domain in space, but an open boundary in time. So propagation problems like this are analogous to initial value problems in ODEs. The solution in the domain of interest is marched forward from the initial state, and it's guided by the boundary conditions over time. So for example, you can see here, this is the temperature on this axis, and this is the space along the bar, for example, and then you can see over time this changes, so that it marches forward in time, and then we reach eventually some steady state. This is another example where here is our space, and this is again the temperature, and you can see kind of how this changes over time. So let's look at another example. We've got the equation here, partial to u by partial t squared equals c squared, partial to u by partial x squared, where c greater than 0. So here a is equal to c squared, b is equal to 0, and c is equal to minus 1. So b squared minus 4ac is equal to 0 minus 4c squared times minus 1, which is greater than 0, which means this is a hyperbolic PDE. So the characteristics are again found by performing the characteristic analysis. So we put these equations into matrix form, we set the determinant of the matrix equal to 0, and we can solve for dx dt, which in this case is plus or minus c. So this means that the characteristic paths are straight lines with the slope plus or minus c. And the speed of propagation of information along these characteristic paths is, again, plus or minus c. So the information propagates at a speed of c along these characteristic paths. So this is known as the 1D wave equation. And so, for example, we can consider the vibrations of a thin uniform elastic string fixed at both ends, and this is governed by the wave equation. So at time is equal to 0, the string is slightly displaced with some initial condition, and then it's released from this displaced condition, and we can see what happens over time. So the initial condition is given by the initial shape, which is some function of x, and it is released from rest. The boundary conditions can be given at the ends of the domain in this case, and are held or are prescribed for all time. So this is an example of the solution of the 1D wave equation over time. So we've got these two characteristic paths, one moving plus c and one moving minus c. So those are shown by the red and the green lines, the positive traveling wave and the negative traveling wave, and then the blue is the total wave. And so you can see kind of how those, the blue and the red and the green add up to equal the blue. So it's important to discuss a little bit about the initial values and the boundary conditions. So a differential equation governs a family of solutions, and the particular member of the family that we're interested in is specified by the auxiliary conditions that are imposed on the equation. So for steady state equilibrium problems, the auxiliary conditions consist of boundary conditions on the entire boundary of the closed solution domain. There are three types of boundary conditions that can be imposed. There's the Dirichlet boundary condition, where the value of the function is specified. So f is specified on the entire boundary. There's Newman boundary conditions, where the value of the derivative normal to the boundary is specified. So for example, partial f by partial n is specified on the boundary. And there are mixed boundary conditions, where we have a combination of the function and its normal derivative specified. So for example, we could have af plus b partial f by partial n is specified on the boundary. For unsteady or propagation problems, the auxiliary conditions consist of initial conditions along the time or time-like boundary, as well as boundary conditions on the physical boundaries of the solution domain. So here we can have boundary conditions on the physical domain. We can have an initial condition specified, and then we have this open boundary in time where our solution can march forward in time.